Go ahead, JW.
Hello, everybody. My name is JW Thompson of ADEQ, and here today we're doing our delegated agency training, our first one of 2025. Our topic is going to be how to design and review an on-site wastewater treatment facility for a truck stop with a restaurant. This will most likely be a multi-part training because there is so much information here, but it is going to be a fantastic series. Our presenters are Raymond Morgan with ADEQ and Mike Sidham, VP of Easy Treat. They'll go into their own introductions and let you guys know more about themselves. Take it away, Ray.
Thank you, JW. I appreciate that introduction. Good afternoon. For those who don't know me, I'm Raymond Morgan, a professional engineer who is retired from ADEQ, and I've came back to work as a contractor, do training and other needed tasks. So Mike, why don't you go ahead and introduce yourself now, please.
Thank you. I'm Michael Stidham. I'm the Vice President of Easy Treat. I've been in the wastewater industry for approximately 37 years. My responsibilities are engineering assistance, regulatory assistance, and design criterias for these type facilities with high strength waste as well as residential systems. So hopefully we'll have a great presentation for y'all. Please feel free to ask any questions as we go through the presentation.
Thank you, Mike. Let's look. The first thing we're going to do, we're going to look at Arizona Administrative Code, called the Arizona Administrative Code Review. The designs that are done for this type of facility right now fall under the, well, probably 4.23 permit. They need to be done consistent with what the Arizona Administrative Code says that you're to do, and they need to follow good engineering practices. We're going to cover different elements of that engineering practice in subsequent slides, but I thought I would start out and give you a picture of the Capitol building in Phoenix. For you, if you haven't ever been up there, that's what our beautiful Capitol building looks like. Now, let's start out. This first section is, instead of me saying R18-9-A309.A7, I'm just going to abbreviate that and just you add in the R18-9. So we're going to look at A309-A7. And there's some very important things that we want to note here. Is that, first of all, a person, notice I bolded some key things, key words, shall design and operate the permitted on-site wastewater treatment facility so that, notice both the design and the operation are to be consistent with this section of rule. But I want to zero in on particularly the flows. The flows to the facility consist of typical sewage. And we're going to look at a definition of what typical sewage is, but just to make sure people don't misunderstand, it doesn't include things like motor oil, gasoline, paint, varnish, solvent, pesticide, and so on. Another point I want you to note is that if the sewage contains a component of non-residential flow, such as food preparation, laundry service, or other source, the sewage is adequately pretreated by an interceptor that complies with, A315 or another device authorized by a general permit approved by our department. Because this truck stop has a restaurant, that falls under, needless to say, the category of food preparation. As we'll see later, basically, from the research that I've been able to find so far, all restaurants are high-strength wastewater dischargers and require special treatment, and particularly in the form of what we call the pre-treatment of that wastewater to make it consistent with the wastewater meeting the typical sewage definition. Now, the next section of rule here says, except as provided in subsection A7C, a sewage flow that does not meet the numerical levels for typical sewage is adequately pretreated to meet the numerical levels before entry into an on-site wastewater treatment facility authorized by this article. Now that last phrase, on-site wastewater treatment facility authorized by this article, that's referring to it's permitted. We permit basically primary treatment facilities and secondary treatment facilities. So what it's saying then, before we enter into that permitted treatment process, you've got to pre-treat the wastewater so that it will meet typical sewage that then falls under the regulation of these permitted treatment facilities. And let's look at one other thing. In addition, activities at the site do not adversely affect the operation of the facility. And so you can have a very high strength wastewater that could adversely affect the facility. There are things that could be going on that we're going to look at, like in the restaurant, things that are being used there for disinfection and so on, that could adversely affect that operation of that facility. But notice it doesn't limit, it says activities at the site do not adversely affect. It didn't say activities at the commercial site or at the residential site. The word site is used general and covers all residential as well as commercial. So if a homeowner, for instance, had a water softener and the reject wastewater from that water softener is being discharged to their on-site treatment facility, which may be nothing more than a septic tank, that will adversely affect it. And that is applicable. And we'll touch on this later. Water softener discharges should not be discharged to a treatment plant because it'll kill the bacteria in it and royally mess up the treatment process. Now, I alluded to this earlier. There are some activities that would adversely affect the operation of an on-site wastewater treatment facility. And specifically, the discharge of wastewater containing the following products to that treatment facility will affect it. So for one, I just alluded to it, discharge of a water softener, that's heavy salts, antibacterial agent to the on-site wastewater treatment facility will adversely affect it. Remember, before we had refrigeration, our forefathers used salt to preserve the meat. Why? Salt is an antibacterial agent. Guess what we have in our treatment plants? Both even septic tanks as well as secondary treatment. They're bacteria, either anaerobic or aerobic. So second, you need grease will adversely affect the treatment and disposal field. So you need to make sure that if you use a grease, try to use a grease emulsifier to minimize grease trap cleaning frequency, it will hurt the treatment plant because an emulsifier just keeps the grease from settling out and then goes on into your treatment system itself to coat and mess up everything. So no grease emulsifiers any way, shape, or form. Third, another thing that will hurt the treatment facility, adversely affect it, is the use of quaternary ammonium to disinfect counters, tables, cooking areas, and floors. It's an antibacterial agent. But Mike, I think you mentioned that, are they using quaternary ammonia in the kitchen dishwashing? Could you comment on that, please?
Generally, where you find this practice is when you go into a kitchen in one of these facilities, and they'll have the 3-tub sink. So that 3-tub sink is telling me that they're using quaternary ammonium for sterilization. Quaternary ammonium is a very powerful agent that will, once it reaches your septic tank, it will kill the biology inside that septic tank and prevent the necessary bacteria that you need for nitrification. So we want to absolutely eliminate the quaternary ammonium. In some cases, you'll see that they'll try to use a product called NutriQuat. The problem with using NutriQuat is you have varying flows during the day, and you can't really have a fixed amount of what to put in there for a NutriQuat. So it's still not an appropriate product to use in this situation for an on-site wastewater treatment facility.
Now, Mike, have you had any experience with any of your facilities being upset by quaternary ammonium?
Several times, Ray. One of the biggest ones that I had was an egg facility where they had bird flu, so they disinfected the whole building with quaternary ammonium. and then they introduced quaternary ammonium to where they have clean areas, where they have boots that they have to wash in the tub before they go out there. You'll see it used quite frequently in veterinary equipment places and medical places. So these are, I know that 7-Eleven particularly, it's part of a corporation thing that they require that use their products. And if they have an on-site wastewater treatment facility, you have to inform them that, you know, this is not going to be appropriate. So you want to look at those type places. You'll see it in supermarkets a lot of times too, in the butcher shops. So we have a big disconnect between regulatory in a lot of cases where regulatory may be that the health inspector does the restaurant inside, but we're still on the outside. So the outside folks with the treatment facility don't necessarily communicate with the people on the inside. So a lot of times we've got to find that disconnect and start networking together between what's going on inside and what goes outside. When it goes to a municipal plant, it's out of sight, out of mind. And that same attitude is kind of taken when we have on-site treatment. So that communication between the two regulatory branches, if the person isn't handling both the inside and the outside of the facility, is very necessary.
Thank you, Mike. And Mike points out something, and I'm just carrying this a little bit further. You know, you can have a store or a chain that's used to maybe discharging their wastewater to a public sewer system that goes to a large treatment plant where there's enough dilution in the wastewater to minimize the impact of whatever they're doing in their store in the way of cleaning and disinfecting. But then that disconnect is that when they go into some area that's away where they can't connect to a public sewer, and now they've got a design for an on-site wastewater treatment facility, whether it's just a septic system or it's some type of secondary treatment. Now we got a different environment, and they're going to be tending to do the same thing they would have done in an area that's going to the sewer, and now there's a much more dramatic negative effect. So I think that's something both designers and reviewers need to keep in mind, is the overall background. What is going on? Could they be doing any of this? Can they be carrying over corporate instructions that will result in the upsetting of the treatment process? All right, let's take a look now at our next one, and that is typical sewage. So we have a legal definition of typical sewage. That means sewage conveyed to an on-site wastewater treatment facility in which the total suspended solids content does not exceed 430 milligrams per liter. The 5-day biochemical oxygen demand does not exceed 380 milligrams per liter. The total nitrogen does not exceed 53 milligrams per liter, and the content of oil and grease does not exceed 75 milligrams per liter. The oil and grease, we were a lot of times referred to that as fog, fats, oils, and greases. We had a good presentation on that earlier. So we want to keep those things in mind. And one other area, in A312, there is a requirement. It's called a general design requirement. The applicant shall ensure that the person designing an on-site treatment facility does several things. And I want to call your attention to number 2. That designer needs to locate and design the on-site wastewater treatment facility project using good design judgment and relies on appropriate design methods and calculations. That is a general principle that applies over all design work associated with on-sites. Now, in our individual or in our general permits, or various type 4 general permits, we give a lot of prescriptive information that's giving some guidance in this design. But there's a lot of things that are not covered. And this is where this principle comes into play, is that they need to use appropriate design methods and calculations, good design judgment. And like this presentation itself could fit into one in that category of appropriate design methods and calculations. I'm going to show a lot of things, calculation-wise, information-wise, that help a regulator reviewing a design as well as a designer preparing a design. Now, let's look at a design example for a truck stop with a restaurant. So I like to give a design summary of my approach to doing a design, and I'm going to say I'm a professional engineer. I have a background of doing a variety of designs and so on. I like a design summary. Even if I do calculations later, I put it back, and it gives me a quick overview of my key findings and so on. So we're going to first look at our design flow. We're going to look at it in terms of average design flow as well as peak design flow. So my average design flow is 19,496 gallons per day. So that puts me in the 4.23 category at a minimum. Now I want to use a peaking factor, as we'll see. I'm going to use a peaking factor of 1.25 that's recommended by EPA. So I'm going to, not the 1.25, but some type of peaking factor. So my value is peaking is going to be 24,370 gallons per day. Now, I'm just going to note something here. Right now, we have 4.23 permit that says if you're below 24,000 gallons a day, you're in one category of the 4.23. If you go above 24,000 gallons a day, you're in another category of 4.23. We need to have an internal discussion, ADQ, is to determine what is going to control the break point. Is it going to be the average dry weather flow, or is it going to be the peak dry weather flow? We have not determined that yet. That is a discussion that needs to take place, and further information will be coming along in the near future. All right, my 5-day BOD, that's a composite, because remember, I've got two wastewater streams leaving or heading toward my treatment facility. I got one wastewater stream. It's a high strength wastewater. We're going to look at the details of that. I've got another wastewater stream coming from the service station, the restrooms, that's typical sewage. I've now got to combine those two streams of wastewater and come up with a composite value to do my calculations and the treatment phase of this process. So my summary here, this says my composite value that I've got, concentration is 876 milligrams per liter. That is equivalent to 178 pounds, 5-day BOD. And notice I qualified it at 24,370 gallons per day. Flow determines how many pounds that you're going to have. If I had 15,000 gallons per day, I would have a different pound value. I could still have the same concentration, but I have a different pound value. And I'm going to show you in the formula how we use that flow to determine how many pounds of BOD and total nitrogen. Now, in this case, our total nitrogen loading is 74 milligrams per liter. And as you notice, that's also high strength wastewater. So this wastewater coming into this treatment facility is high strength because of the BOD, and it's high strength because of total nitrogen. And so in that case, we've got an inflow converted 15 pounds of total nitrogen at that 24,000 plus gallons per day. I'm just going to cite some information on soils. We're not going to get to the calculations for sizing the disposal field to a later presentation. But I picked a soil that's a loam with a moderate structure. Its SAR value is 0.6 gallons per day per square foot, and its adjusted value is 1.29 gallons per day per square foot, using a conservative formula that was talked about in a technical work group. And we'll get to that later on. So now, in developing our design of an on-site wastewater treatment facility for a truck stop with a restaurant, we need to keep in mind that we're actually talking about 3 different wastewater flows. And I want to define those below, and I want you to keep those in mind. I've already alluded to a couple of them. First of all, we're talking about design flow in terms of the average daily design flow. And so that's signified by the ADWF, average daily flow. Okay, I've got wet weather in there. Okay, then our second item is a design flow in terms of peak flows with using a peaking factor of 1.25. And basically this is to account for unusually high business volume during the day, the weekends, or the holidays, and that's your PDWF, the peak dry weather flows. Okay, then the third category that I realized as I was working these calculations I needed to define is the treatment capacity flow. In terms of what the wastewater flows that the treatment equipment can process to produce a given quality of effluent. So I just assigned it TCF, treatment capacity flows. And we'll explain the significance of these as we get further in on our presentation. Okay, now what we have here is a pre-treatment flow chart. I want you to stop and think of this whole treatment facility is divided up into a couple of sections. We've got the pre-treatment section, and then when we move out of the pre-treatment section, which is now going to produce a wastewater that meets the definition of typical sewage, we move into what I call the final treatment. You could call that the permitted treatment because that falls under our type 4 general permits. And then that final treatment, there's a couple of subcategories called primary treatment and secondary treatment. We'll look at another flow chart for that. And where I'm seeing designs, they mess up. You need this pre-treatment needs to have a hard line. There's no wastewater flow cycling back into pre-treatment. The raw wastewater comes in, goes through the pre-treatment process, and then leaves the treatment process to move into that final treatment or the permitted treatment zone. So Mike is going to explain a little bit more about what's going on in this pre-treatment flow chart. Mike, you want to go ahead and take it from here and kind of explain what we're looking at?
Okay, so at the front of the train here, we start with the grease interceptor grease trap. That's going to take all your kitchen waste, and it's going to merge itself into the domestic line labeled as typical restroom wastewater. And from there, we may have a wastewater pump station, or it may be gravity flow. So at that point, what Ray has laid out here for us right now is 2 trains of septic tanks. These are your biological digesters. And in this terms here, retention time. The one thing I like about Arizona is they require a minimum of 2.1 times daily flow for that primary treatment. And with that, with retention time, if we have baffles in each of these tanks, and we're going to have septic tank effluent filters. The septic tank effluent filters are typically a 1/16 slot filter in there that help remove solids. So we're going to collect more solids in the first primary tank, and then the secondary tank, we're also going to have a baffle in there, and we're going to have a effluent filter on those 2 as well. From there, we would gravity feed into our treatment components, and in this case, we would be using for 4.23 is recirculating media filters. So there are several brands of media filters out there, but what we're looking at here is a total capacity of 27,000 gallons of treatment pods on this flow diagram. Once it's recirced, we go into our final recirc pump tank that's going to continue to recirc back to these pods, but we're also returning a portion of that water back to an anoxic area, which would be downstream of your first primary tank. We need the anoxic area. Once we go through the recirculating media filters, so we have proper alkalinity, that's where we're going to take care of the nitrification process and converting the ammonia to nitrates. Once we're into the recirc flow tank and recircing back, we're going to recirc the nitrified water back to this anoxic area, where we're going to exchange the oxygen with the carbon and release our nitrates into a gaseous form. And you'll see the flow equalization pump that Ray has there is basically in mind of going to your drain field and such. And keep in mind that in the testing, third-party testing of these systems that we do is typically through NSF or another certified body. The flows that are coming from these testing centers are already equalized. You get so many gallons per hour, you get so many gallons per event. We don't have that luxury with this facility as a truck stop. It's a 24/7, and we're going to have peak sessions and things like that. So later on in this presentation, we're going to address that too as well. But in your asterisks there, the septic tanks with the baffle and a septic filter. On the grease trap, we're going to use a grease trap filter. That grease trap filter is a 1/16 slot. So it's a more finer process on keeping the solids and fats, oils, and grease from reaching that domestic line. I strongly urge of having a frost-free spigot out there at some point, and typically the operator will have a water hose out there. There'll be one supplied, and they'll have the ability to clean these filters on their service the days they're out there on the service. We have to keep the filters clean quite often, so we don't have a backup in the treatment train. If the wastewater pumping station is used, we really want to avoid a grinder pump. The grinder pump with this type technology masticates the sewage, and at that time, you're probably going to have to put in more pre-treatment to be able to separate the solids. So a solids handling pump would be the more appropriate item to use there. Other times we find ourselves a lot of times downstream as a gravity system. So it'll either have some sort of transfer or it'll have some sort of gravity flow, so the one thing that we find out here in the systems that we're doing in Arizona, when these are designed with gravity, which is the typical 4.01 general permit there, we wind up getting extremely deep in the ground with these primary treatment tanks. And I've seen them in the ground as far as 9, 10, 11, 12 foot in the ground. We want to avoid that if we can. That's when the pump system would come into play to try to keep that elevation up. Being able to retrieve those filters when they're 10 foot in the ground sometimes becomes quite a feat and creates additional maintenance for us. So anything that we can do to try to keep that primary treatment and up to where it's within a few feet of the ground is going to be our ultimate solution here. I don't think I missed anything. You have something else to add there, Ray?
Yeah, I just want to stress that we do not have a permit for the pre-treatment phase. We don't have detailed prescriptive guidance for what goes in the pre-treatment phase. But the pre-treatment phase is just governed with a general statement that you're to do things following good engineering practices and procedures and calculations and so on. I cited that earlier. And so if a designer is presenting something to a delegated agency, they need to be able to demonstrate information like this and calculations like we're going to go over, because that is good engineering practice. It's not like just somebody just plucking stuff out of the air. There's good engineering procedures, logic, and basis for doing whatever is done in there. And they need to be able to project, be able to determine what is your influent wastewater strength, what is your effluent wastewater strength, what's the strength of the wastewater going out, does it meet typical wastewater, typical sewage. So we'll get into that in a lot more detail. Okay. So what we have here is just a picture of three tanks in series, and I picked this picture out to illustrate a few things. I want you to note what is missing from this drawing. There's no anti-buoyancy measures that's been installed. I'd like to think that they're going to ultimately do this, and I just really want to encourage reviewers, and then later if any designers are looking at this, you need to consider buoyancy calculations for your facility. It's actually mandated if it's for a permit that falls under the 4.03 to the 4.23. It's required to do that. And sometimes people forget that you can have a combination of bad events. And so you say, well, my concrete tank is so much weight, I've got to be filled with wastewater, solids, whatever. But then they forget that tank gets pumped periodically. And so if we have the right set of circumstances where it's pumped and then water is able to get up to start exerting buoyant forces, then the tank could be affected and lifted. And I had personal experience of this when I worked with Pima County Wastewater. We had a series of service water tanks of what was then called the Ina Road Wastewater Treatment Plant. Engineer did the design. These tanks, they were to hold service water. Fancy word saying there's effluent that could be used for washing sledge hauling trucks and capture that and take it back to the treatment plant. And the engineers had put gravel down the sides and bedded it, and they brought the gravel all the way up to the surface. And then at Ina Road, the soil is pretty tight there. It's kind of a clay soil. So we had a big, large storm event. And so those tanks were located near a grader ditch that was collecting stormwater to channel it on off site. And it overflowed the grader ditch, and the stormwater started going into the gravel, and it filled up the voids. All those concrete surface water tanks popped out of the ground. They were sitting cockeyed out of the ground because they were not full of water, and the buoyant forces were greater than the weight, and they popped them all out. At the time, Pima County held the engineer responsible for having to redo their design and pay for the costs of putting those tanks back underground again and fixing everything. So the total cost went to the designer to make that correction. A better design would have been to put some anchors along the side so no matter what, those tanks can't float, or at a minimum, stop the gravel about 2 feet below the finished grade and put some type of sealing soil, maybe native, maybe even more sealing than native, so that no water can get to that gravel. Because if water gets to that gravel and gets in that void area, and you've got a partially empty tank, it might be able to, the buoyant forces might be able to lift it out of the ground. So that's just an additional training item I just wanted to point out. All right, now this is a flow chart showing the final treatment, also I call the permitted treatment, and we see the two categories, primary and secondary treatment. And so maybe, Mike, you can explain what we're seeing here.
Again, your pre-treatment is your septic tanks. So with the right amount of retention time with these tanks here, we got a couple advantages the way you have them set up here, Ray. A 6,000 tank followed by a 3,000 gallon tank. So we're going to get, just in reduction in BOD and nitrogen, we're going to, for that retention time, we calculate about 40–45% reduction. Studies out there show it to be a lot higher, but we're very conservative. So basically, we've got 6 points here, six 6,000 tanks and 6 3,000 tanks. So during that retention time, they're all collected into the next thing. We have our recirculation tank 1. That's our anoxic tank. So that's basically going to be a clear effluent in there, but it's still going to be lack of oxygen. And we're going to use that tank there for our nitrate reduction. And that will gravity feed into our recirculation tank. Now, we're showing one recirculation tank here, and by the PPL that I have, we have to have at least 1 times daily flow for recirculation. That can be done in 1 tank, it can be done in 2 tanks, it can be done in multiple tanks, depending on how the stages are set up, in series or parallel. From there, each one of these pods are 5,000 gallons a day treatment capacity based on the PPL. With typical sewage, we should be at typical sewage at this point. and we're going to recirculate into those pods. And typically, our product, we're probably going to be about 6-to-1 ratio as far as recirculation. Depending on the media that's used by the manufacturer, some of them are going to be more of a 3.5-to-1, and it really is based on retention time. So if the media has as you dose this media, how long does it take for the system to drain out? It could be a recirculating sand filter. A recirculating sand filter, typically they're dosing them once an hour. Other products out there probably dose about every half an hour. The media that we've employed allows us a very high rate movement of drainage. So we're able to, dose about, 4 times an hour. And the idea is to get a good coating, and once it completely drains, microdose again. So once we go through and again, we have to have, the correct amount of alkalinity. If you're on a public water supply, typically the alkalinity is withdrawn from there. So I see the alkalinity ranging usually between 19 and 30 on public water supplies. So we're going to have an additional supply for that alkalinity within the system, and that's employed in many different ways. Then during the recirculation, typically it says 7 pounds of alkalinity for 1 pound of nitrogen. So now we're going to, through the recirculation process, we're going to take the ammonia, we're going to convert it to nitrate. Again, that's going to go to our effluent pump station there, and we're going to return a portion of that, typically about 1 times daily flow, back to that recirculation tank 1 anoxic tank and gravity feedback through the system. So what we're looking for is the most nitrified water at the effluent pump station there to return back to that anoxic area. And then from the effluent pump station, it will either gravity feed or be pumped out to your distribution center. But making sure that we have proper carbon through this system and having high strength waste, we're not in any way starving the system for carbon in this. But there are examples out there that you'll see. One of the best examples I could say is a K-5 school. Little kids don't like to go poo at school, so sometimes in other commercial applications, you may find yourself having to do carbon enhancement as well to this, to make sure that you have the proper amount of carbon to convert the nitrate to a gaseous state. You got anything else you'd like to add there, Ray?
Yeah, I believe correct me if I'm wrong, I believe the anoxic tank probably has a little more total carbon in it than the recirculation tank. Am I right in that?
No, that anoxic tank is still going to have a carbonaceous state. It's not going to be solids. It's still going to be a suspended carbonaceous state in there, and it's going to have a very low DO in there.
Right.
We want to bring that when we return back to that tank. We want to bring it to the front of the tank, the inlet side to that tank, so that we have that flow retention time in that tank before it moves back to the recirculation 2 tank.
All right. Well, in a later presentation, we're going to talk in more detail about alkalinity issues, total carbon issues, because in order to get denitrification, the bacteria need the carbon as a food source, and they're going to pull the oxygen off the nitrate molecule, but they're consuming alkalinity in the nitrification process. They're giving up some alkalinity in the denitrification process. And we're going to get into that in more detail in a later presentation. Okay, thank you. Let's look at our next slide here. Now, this is a photo of a project that's using a textile filter treatment process. And that's what the green tanks, those are your treatment pods for the textile filter material in it. And so Mike is familiar with this project, and he's going to maybe tell us a little bit more about it. What do we see in this picture, Mike?
Okay, so what you see in the top right-hand corner is your first septic tank, a concrete tank. Then it's followed by a second septic tank. And then the next 3 tanks are a series of recirculation tanks. And then the final tank closest to the pickup truck is your field distribution tank. So basically you've got three sets of treatment pods there, 8, 8, and 8. And the first set there, you can actually see the 4-inch pipe that's returning back to the first septic tank, the front of the second septic tank. So we're actually recirculating what water goes from those pods back to our anoxic area and bringing it back in. So we're getting the nitrified water in there through those. And the second septic tank, the second recirc tank, which is in the middle there, operates the next 8 pods, and the third one, which would be your right there before the distribution tank, will operate the next 8 tanks. So we've got a system here that's basically built in series, and the different piping networks that we have, instead of using pumps, they're gravity fed back to each of those. So each tank each group of 8 pods, you'll see the way that it's piped in there, that the first 4 pods will go all the way back to the front of the first recirc tank. And then the second set of 4 pods will go through what's called a bypass valve, which will allow basically 80% of the water to go back for recirculation in that tank and 20% to move to the second tank. And again, the process is repeated. The first 4 on the second recirc tank all go back to the front end of that first recirc tank, and the next 4 would be dosed independently back through another bypass valve and continuing on to the third recirc tank with the next 8 pods repeating the process again. And then finally to your final distribution tank. So there is some valving in there, bull run valving, that allows the operator to adjust the flows from the beginning of the treatment train to divert water back to the anoxic area so that they can do the nitrogen reduction. So this one specifically eliminates as many pumps as it can, but it's still, the process is still the same as far as what you're doing with your water back there to return that nitrified water.
All right. How are they handling disposal there, Mike?
Really interesting. There's drip irrigation. So there's 48,000 foot of drip irrigation in the woods there. That was quite an adventure to put in. But this system here, right here, does about 28,000 gallons a day. And it is a little bit higher strength waste. It's actually an RV park, and RV parks are pretty strong too. So this system's been in since 2008, and it's very easy to monitor, easy to maintain, and you know it allows with this typical type design, because it's a seasonal application, that you know that one train can be turned down, or you can turn down 2 trains. So we can adjust the treatment within there by shutting down a part of the plant for the winter period time to meet what the actual flows are out there.
Okay. All right. Let me just add that one of the things we're trying to do in this training is think of the learning as like a 2-step process. First of all, you want to understand the basic concept. Then you want to define more specifics in that basic concept in terms of calculations, more detailed knowledge, and so on. And one of the things hopefully you'll see is that one, you can have a series of pods add up to get your 25, 30, 40,000, whatever flow, and that you just put more parallel trains and then adds up. It's not like you have one giant box to handle 40,000 gallons a day treatment. Like a typical large municipal treatment plant, they'll build some gigantic tank, spend a couple $1 million to build it. Here we got more graduated pods, and as Mike made reference, that if the flow decreases for part of the year, like RV season, RVs are not being like going someplace in the middle of the winter, they can trim that flow back and not have to keep everything fully operational, and then they can add it back on as the flow picks up. So hopefully you can understand the concept and then build on that with more detailed information, which we're going to add some additional things here now as we go forward. So now let's go look at our next few slides here. Let's deal with this restaurant. So the restaurant that we're talking about is a fast food restaurant. As you can see, I've put a label up there at this truck stop. Now, I'm going to pull some slides from an earlier training presentation for those that maybe not be familiar with this, and be reviewed for the others. But we need to note a few things. We got some pretty high strength wastewater in these facilities. Sodas, 79,500 milligrams per liter. Now remember, the max BOD is 380. So here's some soda, 79,500. That can raise the BOD value of a lot of water up to exceed what the 380 milligram per liter value for typical sewage. We have beer, 80,000. So there's a tavern or a cocktail lounge, whatever, all of that beer, alcohol, whatever, that's going down the drain, spillage, that's high strength. Whiskey, coffee is every bit as strong. Whole milk, 104,600. Skim milk, 67,000. All of that milligram per liter of BOD. That's why I said earlier, I believe basically all restaurants are high strength wastewater dischargers, and we need to keep that in mind and require P treatment. I don't care whether it's on its way to a septic tank or on its way to some secondary treatment. It's a high strength wastewater. They need to be pre-treated to bring it down to the level of typical sewage. And so we have a range, and I've selected the fast food one with a BOD of 2,137 milligrams per liter. It could be all the way down to seafood at 555 milligrams per liter. And that was a 2013 study done by the Harris County Public Infrastructure Department in Texas. There's another study I think is relevant. This is done by the Texas Restaurant Wastewater Analysis, as the Texas Onsite Wastewater Research Council that did this. And there's concern over in Texas about these treatment facilities serving restaurants and having failures. And they came to the conclusion that pre-treatment is necessary to prevent the system failing. And so they went and tracked down, why are our fields failing here? Why is our treatment process failing? And they found they're dealing with high strength wastewater, and that the particular treatment device was not able to handle that. And you had too much carbon going out into the disposal field. Too much carbon means real thick biomat and less percolation. That means field failure. So what they came out with is that the average they discovered was about 1,202 milligrams per liter for their BOD. And then this other one I thought was interesting, and that is you're washing dishes, you're washing your pans and other cooking utensils and stuff. If you hand wash them, your BOD was 2,617 milligrams per liter. Then if you use a commercial dishwasher, it was down to 1,037 milligrams per liter. And I was mulling over about why we might have a higher BOD for hand wash. And I think it's just there's less volume of water. And so all the solids are staying concentrated into a smaller volume of water. So you're going to have a higher concentration. That's my guess. But as Mike had mentioned earlier, there's some cautions and concerns about commercial dishwashers. Got to make sure that no place that they use emulsifiers or quaternary ammonium, things like that, that can also affect that. Is there anything additional you want to add, Mike, on this issue of high-strength wastewater or dishwashers and so on?
Yeah, the dishwashers are an issue. What we've had in our industry, and again, if you're on a municipal system, you know, it's gone, but on an on-site system, so if you got a commercial dishwasher, right now, they've got companies out there that will basically lease you the dishwasher for $1 a month if you buy the chemicals from them. A lot of them you see are like behind bars, the little dishwashers, low temperature, high efficiency. What that means is they've lowered it from washing temperatures from 180 degrees down to 110 degrees. And that's when you know that they're using emulsifiers. It's usually a red liquid that's going into the machine for a quick, inspection to see what it is. So the emulsifiers, what they do is, a good example is if you take a bucket of water and you set it out in 32-degree weather, it's going to freeze. I'm like most people, I like to save my bacon grease. It'll freeze on sitting in room temperature. When they add the emulsifier in it, then it lowers the freezing temperature of the grease. So if you take water and you add salt to that water, it's not going to freeze until 18 degrees, as opposed to grease freezing at room temperature, lowering that temperature of that grease. It'll flow through that grease trap and it'll go through the grease trap filters and it'll go to your main treatment center and cause a lot of problems. So the first thing you want to look for is, or specify no low temperature, high efficiency dishwashers on an on-site wastewater treatment facility. That's a guaranteed thing that they're using emulsifiers. In the hand wash area, the thing to look for again is the triple sinks. When you see the triple sinks, you want to investigate what kind of chemicals they're using for sterilization, and most of the time it's going to be the quaternary ammonium.
Okay, thank you, Mike, for that insight. Okay, now we need to determine what our design flow is. And so we're going to be using values from Table 1 to do these calculations. And so we look at the first category, and that's the service station, also known as a truck stop, with toilet facilities. And so the first bay, you figure 1,000 gallons per day, each additional bay, 500 gallons a day. So by the bay here, we're also looking at where you're stopping to gas up. That's the bay. And so the total flow we got from there is 14,000 gallons per day. And so these values are just average dry weather flow values. Okay, the restaurant with toilet facilities now. So we're looking at, we got 6 employees, 20 gallons per day per employee. That's 120 gallons per day. Now then the kitchen waste and disposal. So we need to make a determination of how many meals we're going to serve. So we're saying we're going to serve 384 meals in 16 hours times 7 gallons per day per meal. That's equal to 2,680 gallons per day. We're going to assume that it's 1 customer per meal, and that's going to be 387 customers times 7 gallons per day. Per customer, that's 3,688 gallons per day. Now this is where I would encourage the designers and regulators to very carefully look at the information that's been given to you to do this calculation. We don't want to have somebody says, oh, I'm a little high on my flow. I'm over 24,000 gallons or whatever. All right, let me go back. Let's cut meals in half. Let's cut the customers in half. Is that good engineering practice? Is that really realistic for what's taking place there? Because what you could do, you could be undersizing your treatment process, undersizing your subsequent disposal field, and you're setting yourself up for a failed treatment and disposal process, which is going to be a nightmare for the owner of that facility. And so, the designers need to recognize this and say, look, we need a good, honest estimate, because if we're wrong on this, we could have a far worse problem down the road with a failed treatment and disposal system. So it's like really, really important. Now, our design flow, we looked at both average and peak flows. And so let's come up with our average flow now. We have our 14,000 gallons per day plus 120 gallons per day plus 2,680 gallons per day plus 3,688. That gives me 19,496 gallons per day average dry weather flow. Okay, my peak design flow now, I'm using my 1.25 peaking factor. That gives me 24,370 gallons per day. So that's what I would need to go through for coming up with determining my design flow. Now let's go and let's start our next level of calculations.
5-minute warning, right?
5-minute warning. Okay, let me stop a minute. Do we have any questions right now? If you got any questions, I forgot to mention.
We do have a few questions in the chat, so this might be a good stopping point.
Okay, that's what we're going to do then. We'll stop here, and in fact, I'm going to back up. All right, let's see if we can address those questions in chat. Why don't you?
Or I'll start reading them out for you and Mike to address.
Yes.
So we have a couple of questions. They're basically asking the same thing. You know, what is a good sanitizer to use in the triple sinks that's, you know, won't cause any problems with an on-site system that's not the quaternary ammonia?
You know, a lot of facilities use, there are septic friendly sanitizers out there. One of the things that I see used a lot, because we are separating into a grease trap, is the accelerated hydrogen peroxide. With a proper retention time in the grease trap, then the accelerated hydrogen peroxide is going to dissipate into a gaseous state. If you have a problem with it, and you have a problem with the grease trap, and I always try to recommend that the designer use not one grease trap, but two. So you have the 4-to-1 length ratio in the grease trap plus the retention time, and baffle the grease trap. The more retention time you have, the more capability you have of releasing that peroxide if you're using it, and not making it to the primary treatment. But it also gives you the ambient temperature of the ground and more surface area to coagulate the grease, as far as how we would do that. But you know, the chemical companies, when they talk to these owners of these facilities, they do have, you know, sanitizers that will not harm the septic tank issues.
Okay, it looks like, all right, the next question, why no TSS value? We're designing the treatment facility around the BOD, organic loading, and the total nitrogen or loading. Did you have any comments on that, Mike, about what you see in terms of the design process?
You know, really not so much in the TSS. With the 4.23, the technology is really the difference, because you're using, you know, media filter technology as opposed to using a aerobic treatment unit process. You know, an aerobic treatment process where you're adding the air, you're creating an activated sludge, you're creating more solids, and it typically traps methane gas, which will cause the system to burp and let TSS move down the drain. So there's a big difference in the technologies as far as that's gone. With the proper retention time, as far as the solids are, with the tanks at 2.1 or better in daily flow, you've got enough time in there for retention to actually separate those solids out. So we don't typically, in our technology, the recirculating media technology, find big problems with suspended solids unless the system does not have some sort of equalization as far as the flow. If you can control the equalization of the flow through the system, then you're not basically blowing out your septic tanks. So you don't see a big problem with the suspended solids. Where people have a misconception about suspended solids is it is attached growth. And as that growth breaks off, we have a process called sloughing. So you will build up, some what's appearing to be solids inside the recirculating tank, but it was actually good bacteria, which is refed back up to, these pods. Is what I find.
Okay, thank you for that insight. I think our next question is there an interceptor installed? Yeah, there's a grease interceptor, and we're going to go through the calculations for that in a later presentation. We made reference to it in our flow chart. That grease interceptor is required by code, needs to meet the requirements of A315, and so we're going to be going over that in a little bit more detail later. Then another question here is, what is a good source for a good, honest estimate of meals served? So I think that is going to be varies depending on the particular establishment. Brand X restaurant should have some information about that versus brand Y, depending on what type of food. Is it a sit down? Is it more limited, or is it a more high volume fast food type place? ADQ does not have a specific notation prescriptive guideline for that. This is going to go back to that. What is good engineering judgment principle? What is the basis for that? And that's something the designers should provide along with their design, explaining where did this come from. Mike, did you want to add anything to that? Are you aware of any possible references that are out there on that topic?
This is a discussion we have with designers on a daily basis, and it becomes a discussion between the owner, again, trying to downsize the cost all the time. So my recommendation is, Ray and I spoke about this very briefly, is I want to see in the design criteria, I want the engineer to call out exactly what they're saying, that this is how many meals a day. Is it morning, lunch, or breakfast, lunch, and dinner? Is it open 7 days a week? These are the questions I'm going to be asking. How many chairs they have there? And then the engineer actually put down not to exceed limits. And if those limits are exceeded, then we can go back to the original permit, and it would be an issue between the owner and the engineer at that point. So when we talk up to the engineers about it, they start becoming more aware, but the conversation just doesn't come up very often of trying to decide what that is in most states. And I saw a place in Strawberry, they told me it was just this many seats, and then you go outside and there's 16 more picnic tables that's not being counted. Well, that counts too as well, because people are using the restroom, you're doing things. So it does become a difficult thing. I'm hoping in the new 1.5 rules that we can address a little bit more of what goes into that design protocol from the engineer submitting it into permit for notice of intent. And then it kind of holds everybody's feet to the fire.
Thank you, Mike, for that explanation there. Let's look at this next question. Could you please explain how the example design would comply with R18-9-A314-1C, which indicates only 2 tanks are to be used as a single unit, with the first one being 2/3 of capacity. This indicates separating flows into multiple primary tanks. Admittedly, not allowing this would lead to a gigantic tank, and it's not realistic. Maybe a code clarification on septic tanks in series would be helpful. Let me let me just mention something here, and I've stated a lot before. Whatever your assumptions, if you've got a valid assumption, you're going to probably have a valid conclusion. If you have a poor or improper assumption, you're going to have a poor or improper decision. And I think the underlying assumption here is that the design flow has to all proceed down one train through one or two septic tanks. And nowhere in rule does it say that. What we're taking is a total design flow, and we're doing an equal split and putting a portion of that flow through the various treatment trains. And that in each treatment train, and rule says specifically, septic tanks placed in series are considered a unit and meet the same criteria as a single tank. So what we're doing, that first tank, 6,000 gallons, was 2/3 of the total flow for that particular treatment train. And then the 3,000 gallons is 1/3 of the flow. So the design flow doesn't have to go into a single row of tanks. It can be split up, and it would be just fine. Next question. Chlorine, iodine, and quaternary ammonia quats are the only FDA-approved sanitizers. Of those, which one is best for a septic? How would you, Mike, what do you think about that? How would we answer that if you were going to answer it now? Not that we have to answer it now. We can, that's something that we can provide some answers later.
I've read that same statement before, but again, the publication that they had there is quite outdated, I believe. And, you know, we've just moved so far along with having materials as we understand how these things actually, you know, affect these on-site systems. On-site systems, when a lot of the EPA stuff was written, was really not such a big industry, a very minute, but it's becoming a very big part of our community now, as we outlie into further areas. But you know, it's a difficult question. I know counties say the same thing about the health on the inside, you know, cleaning and sanitizing, but there's really no, it's just not a good answer for on-site wastewater treatment facilities to use those chemicals. Like I said, the chemical companies out there right now, they have a lot of septic friendly products out there that do sanitize. And I often tell the owners to reach out to these other companies and see what they have and process that. I'm not a real big expert of what's going on in a restaurant. I'm really know what the effects are on the outside once it comes out of the facility.
Okay, thank you. If we have, that's something we'll keep in mind. I was not aware of that issue. Trying to find something that's compatible as a sanitizer, and then something that's also compatible with the downstream treatment process that won't adversely hurt it. And it may be that the chlorine does not have as much of an impact as quaternary ammonia has, because as soon as chlorine makes contact with a carbon particle, it's going to create a chemical reaction to oxidize it. And that actually might be neutralized a little quicker than maybe quaternary ammonium. But that's something that definitely bears looking at a little closer. And we'll need to make note of that for future reference and presentations. Then I think we got one last question. What do you use to split the design flow into multiple trains? And okay, basically you got either gravity flow or you got pressure flow. And so the gravity flow, you would, if you did it like a typical distribution box, have all the inverts at the same, and then have it going into one tank, then it just split and goes out. If it's that would be one approach. If it is a pressure distribution, then what you need to do is equalize the pressure and your different trains. So you need to have a pressure gauge and a closure valve so that you can regulate the pressure so that you should be dispersing equal flow to them. But that is a design issue that, and it's a very valid point, you don't want to overload one train or the other. It has to be equally loaded so you get appropriate treatment. And that's a very good question. All right, looks like a couple more came in. Can ADEQ get the ADHS to resolve the disinfection question? Well, we'll take that back and we'll see what we can do on that. Chlorine would dissipate quicker than quats. Monitor pH to see if okay. That was my initial gut reaction, is chlorine would be the easier one to use and could dissipate and maybe not have as much of a problem with it. And a good point, monitor your pH to see if it's okay. So ideally our effluent, ideally the wastewater coming in is between a pH of 6 and 9, and definitely the effluent going out is between a pH of 6 and 9. Okay. I believe we're at an end, and thank you very much for your attendance. I hope this has been informative, and we'll be able to continue this discussion in our next training session, which I'm looking at sometime the end of March. And feel free to reach out to ADEQ if you have particular questions or issues on this, and we'll do what we can to try to provide some help and guidance to you. Thank you again for attending.